This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. Hope you had a good weekend. It seems you had a very good weekend. So bipolar transistor models. We discussed about small signal model in the last lecture. I have shown you how to draw a small signal model. Then I will go through the slide part. I used a document camera in the last lecture. Today I will go through the slides. Oh, is it locked now? Yeah, maybe I locked it. Keep it open. So there are two types of transistor models. One is a bipolar transistor large signal model. Another second one is a small signal model. Large signal model, which I already discussed in the previous lecture, if the bias points changes, then we call it as a large signal model. Large signal model most of the time happens when you connect a large voltage at the input. Then your bias points changes, like your VC changes, and if that is the case, that is called a large signal model. So if you want to represent a large signal model, the model can be used for arbitrarily large voltage and current. Obviously, when voltage is high, the current is high. Changes in the transistor, provided device operates in the active region. So when your transistor is operating in the active region, if you connect a large input signal, what will happen is your DC bias points, maybe I should use the word DC, your DC bias points will change, like your VC. VC you set to 1 volt, that is a DC VC, that is voltage between this point, the collector and the emitter. But then what will happen is when you connect a very large input voltage, the DC bias points will change, fluctuate. If that is the case, you are operating your transistor in a large signal mode. And then we draw large signal model. And then if your signal changes the bias points, here I have written in the bracket, the transistor operates in the large signal domain. Bias points will like a VC. When VC is fluctuating, your DC, IC will change, collector current will change. So then we represent something like this. A diode is placed between base and emitter. So base and emitter, we place a diode. And a voltage controlled current source between collector and the emitter. I already discussed what is a current source, and then transistor is a voltage controlled current source. So that is the reason we represent this one here, and then this current source, the current through this current source is determined by this voltage, how much voltage you apply here, VB. So that is the reason IS exponential VB by VT. VT is the thermal voltage. That is a constant 26 millivolt at room temperature. And a voltage controlled current source is placed between the collector and the emitter. So this is a simple representation of a transistor operating in the large signal model. So large signal model, you can see we replaced the input here with a diode. This is a representation for the large signal. We don't have to study large signal here because we will be using your transistor as an amplifier, and then we use that amplifier configuration for making operation amplifiers. So we don't have to study large signal, but you should be knowing what is large signal. Again, we already studied the characteristics of bipolar transistor. I have written here without early effect, means we are not taking into account the output impedance. And then if you want to plot IC versus VB, voltage between base and the emitter, and then you want to measure the collector current, then you can vary this VB here. You connect a voltmeter here, and then you can vary your voltage, connect a voltage source here, and then you vary the amplitude. Then the voltmeter, you don't need a voltmeter. The voltage source will give you the reading. And then you can connect a current meter here, and then you can measure the current. Then you can plot VB versus IC. Anyway, you will be doing this in the lab this week. Then if you want to measure IC versus VC, then again you vary the VC here. Means you will be varying your VCC. And then you connect a resistor here, then you can plot it. These things I already discussed in the previous lectures. This graph also I already discussed. You can see here IC versus VB. When your VB is 700 millivolt, your IC equal to around 24.6 microamps for a given bias. And then you can see when it is 750, see there is a small change, only 50 millivolt change. Then you can see that your IC is 169 microamps. It's a large variation because of this exponential behavior. Means your collector current equal to IS into exponential VB by VT. Yes, very small change in your input voltage can create a very large collector current because of the exponential. So this graph is obvious. See, 800 millivolt, only 100 millivolt difference, but then you can see that it's became 1.15 milliamps. See, 24.6 microamps to 1.153 milliamps. Big variation in the collector. And then this shows, I haven't shown this region. This is this will be like coming, and then it's coming to here. Then from here it is coming to here. From here, from the origin it is coming to here. That is in the saturation region. Here I have drawn only the active region. So in the active region, you can see that when your VC is changing, your IC is almost constant. So that is the reason we call it as a current source. I already discussed the current source. The current source keep current constant irrespective of the changes in the voltage or resistance. Large signal and small signal models with early effects. Now we are going to study large signal and small signal models with early effect. So then first we will look at the large signal. So in the previous case, in the large signal, we got the same diagram, but then it was IC equal to IS into exponential VB by VT. So V1 or VB. So whatever the voltage we get here, that is the voltage here. So here V1 is the VB. Then now what we got is an extra term, that is equal to 1 plus VC by VA. So VA is the early voltage. So if you take into account the early effect, your equation for the collector current will change. Means you get an additional term, that is 1 plus VC by VA, and VA is the early voltage. Early effect can be accounted for in large signal models by simply changing the collector current with a correction factor. So you don't have to draw anything extra. The circuit diagram is same, but then you can add a small term here, 1 plus Vc by Va. Then you are taking into account the early effect in the large signal model. But when it comes to small signal model, which we already discussed in the small signal model, well, I will show you a small signal model later, but in the small signal model, you are not only adding this term, but you are putting a resistance also in parallel with the current source, if you recall, with early effect. So, small signal model, again I discussed this in the last lecture. Small signal model. So this is a simple explanation. Small signal model is derived by perturbing voltage difference every two terminals while fixing the third terminal and analyzing the change in the current of all three terminals. Means what it does is, if you want to find out the small signal, you are changing. Perturbing means changing the voltage difference every two terminals. Means you are varying between two terminals. See, this terminal with respect to this ground, or this terminal with respect to this ground. So you are changing this one. Here maybe you are changing your delta V, because this is a VB. If you are varying the VB, means first you got the transistor, you biased the transistor in the correct DC bias region, and then now it is operating in the active region, but you have not connected any signal. But then what we will do is we vary your input delta V, that is equivalent of connecting a small signal that varies with respect to time. The voltage changes with respect to time. So when you have a delta V variation, what will happen is your collector current will change by delta IC, and then the collector current is flowing from here collector through to the emitter. So when the collector current changes, emitter current also changes by delta IE. Then we represent these changes with controlled sources or resistors. So what we will represent is in the small signal model, we will draw it, and then we say that, okay, this is a delta V, and then this is a current change using the current source. I will come to that point. So the basic idea is we are changing something in the circuit. So small signal, so this is, you have to be careful with the small signal. The small signal model is relevant only if your signal is changing. Please remember that one. That is a very simple thing, but often students forget. Small signal model is relevant only when the signal changes. If the signal changes with respect to time, then there is a small signal. If signal not changing with respect to time, you don't have any small signal model. So the circuit, small signal circuit is relevant or will come into picture when your signal is changing with respect to time. Small signal model, there are some rules for the small signal. So small signal model, in the last lecture I discussed about drawing the small signal model of a transistor, one just transistor. But when we have big circuit, then we will be drawing small signal model for the entire circuit. I think I have shown you an example for the full circuit. So when I draw the full circuit, there are some rules you can follow. That is called a small signal model, some rules. The sources are set to 0, means all the voltage sources set to 0, current sources, voltage sources, mainly this is, I am talking about voltage sources. All the sources are set to 0. Why sources are set to 0? Because the voltage source not changing with respect to time. So that's the reason we set to 0. Is used to study response of the circuit, small signals, and compute parameters such as gain, input, output, impedances, etc. So if you got a voltage source in your circuit, we will set that as 0. I'll show you an example. Then replace all the capacitors by short circuit. Why we replace all the capacitors by short circuit? Because we are dealing with the signal, some signal that is changing with respect to time. So capacitor is open for DC, but capacitor is a short for signal. You know what I meant? So if you take a capacitor, so capacitor, so this is a simple capacitor. So capacitor means you got two plates that is separated by some distance, and then this is a capacitor. So impedance of the capacitor, that is equal to maybe XC, 1 by 2 pi FC. So F is the frequency. For DC, so if you connect a DC voltage here, what will happen is you connect a DC voltage. So if you connect a DC voltage, what is the frequency? that is equal to 0. So means your impedance equal to infinity, means this capacitor will block DC. But then when you have a signal, so signal means you will be representing like this. So when you have a signal, then you have got your capacitor, then what by 2 pi fc. So if you got a signal frequency, maybe the frequency is higher, then what will happen is this term is very, very small. So that is the reason when you are dealing with the signal, we take it as a short, especially in the small signal region. We take this as a short because for the signal, when there is a frequency, this is the value here, the impedance is small. Actually, when f equal to infinity, at very high frequency, impedance equal to 0, because your x equal to 0 means it is a short. But then here we are not dealing with f equal to infinity, but still we regard your signal is having some high frequency, and hence this value, the impedance here is very, very small. That is the reason we take it as a short for small signal, because we are dealing with a signal that is changing with respect to time. Inductors by open circuit. If you know the capacitor, the inductor operation is just by reverse. Capacity impedance equal to 1 by 2 pi fc, but then inductive impedance, what is the value? Directly proportional to frequency. That is the reason it is open circuit, other way around the capacitor. The DC voltage sources by ground, DC voltage sources, because when signal is passing through the DC source, and then it is not seeing any impedance. So DC voltage sources, that is not seeing any impedance, plus your DC voltage source means you are connecting a 5 volt from a power supply that is not changing with respect to time. So we put it as a ground. And DC current sources by open circuit. If you got a DC constant current source, we put it as open circuit. So we will follow these rules. These rules are very simple. I will show you some examples. So replace all the capacitors by short circuit, inductors by open circuit, DC voltage sources by ground because it is not changing with respect to time. Again, DC current sources not changing with respect to time. Capacitor is acting as a short because of very small impedance. Inductor is open because it will act as a very large impedance because the equation is equal to directly proportional to frequency. Here it is 1 by frequency, inversely proportional to frequency. So again, this is a circuit, and then now we will not connect the power supply, rather we will draw something like this and say VCC. So when you connecting your VCC means here you got the voltage, positive voltage, and there is a ground. But then this is an easy way of representing. Means what I meant is we will not be drawing the power supply. So you got the transistor, and then this is NPN. So this NPN. So here, in order to keep it reverse bias, you have to connect a power supply, something like this. And then here you ground it, here your VB. So but then we are not going to draw like this. So rather we will just draw VCC, because that is easy in the circuit when you draw it. And then when you are taking this part, input part, so you have got R pi, input impedance, and voltage drop across R pi is represented as a V pi, which I already discussed, and then this is a ground, this ground. And then this part, that is between collector and the emitter. So between collector and the emitter, we got a current source, because transistor is a voltage controlled current source, which I already discussed. Why there is a current source? Because in the diagram, when you have the VC versus IC, it is like this. So this is active region. So in the active region, your voltage is changing, but your current is not at all changing much. Little change because of the early effect. That's all. So this region is like a current source. Current source means some device that will not allow it to change the current. Means current will keep constant. So that's the reason we call it as a voltage controlled current source, transistor. And then, so between collector and the emitter, we will be having a current source. See, GM V pi. GM is the transconductance times V pi. That is a collector current. Because what is a transconductance? Transconductance equal to collector current divided by VB, or collector current equal to GM into VB. So here VB, here is a V pi. So GM into V pi, that is a IC here. So then this is a VCC is a constant voltage source. So we keep it as 0, means we ground it in the small signal. You know what I meant? That is the reason the rule here we read DC voltage sources by ground connection. See, we are grounding the DC voltage sources. If you got a current source, we will be putting as an open circuit. And then, so when we combine it, this is a small signal model. So this is a V in, so you can write here V in. So here V in, and then this is a base, this is emitter, then you got R pi between base and the emitter, then the emitter is grounded, and then between collector and the emitter you got a current source, this current source Gm into V pi. Then as per the rule, if you got a constant DC voltage, that is VCC, that we ground it. So RC grounded. But then this is a small signal model, we haven't taken into account Early effect. See, without Early effect. So with the Early effect, which I already discussed, you will be having an arrow here across the current source. Then I have a question. So here I already mentioned, if you go back to the rule, the current sources by open circuit. But then here you got a current source, then I haven't put this as open. Why? Yeah, so this current source is not a constant current source, because this voltage source is a constant one. You bias it and then you are connecting to your power supply, maybe you set it to 5 volt. That is not going to change it. But then if you got another current source designed, a constant current source, you can design a constant current source. Maybe you design one, and if you connect it, maybe you design it for 1 milliamps and connect it. If that is not changing with respect to time, then you keep it open. But this current source, the issue is this current source, if you look at the equation, Gm into V pi, so this is a dependent current source, means when your V pi changes, this current source changes. So this is not a constant current source. So that is the reason we are not keeping it as open. So with Early effect, input part, there is no difference. Then the output part, you will be having an arrow that is coming in parallel with your current source. So because the current source, the ideal current source got infinite impedance. Ideal current source. So what is it? I discussed the current source. So what is a current source? So current source is a device that keeps your current constant. Means I already discussed the C. So this is a simple example. So you got 3 volt, and this voltage you can vary. This is your R. When you are plotting your IV characteristics, this is your current, this is your voltage. Then you get a slope depending upon the value of this R. The slope here is the R value. So that is a Ohm's law. But then if you are connecting a current source, so I am going to connect a current source. You can design current source using transistor. You can design with op amp. So we represent a current source as something like this, and then this arrow represent the direction of the current. So we can design current source maybe for 1 milliamps. Then what will happen is, so this is 1 milliamps. If it is an ideal current source, then what will happen is you vary your voltage, you vary your resistance. Then what will happen is the current source will make sure that this is always 1 milliamps. So that's called a current source. So current source we can use for making a means you can use current source for many applications. If you want to drive a laser diode, I told you laser diode, if you connect to a simple circuit, it can damage if there is a fluctuation. So you can connect a laser diode here, that will make current constant. But then current source got infinite impedance, ideal current source. How can you say current source got infinite impedance? Because your Ohm's law V equal to I into R. So what is R? R equal to V by I. Means if there is a delta V, delta I. So here what is delta I, delta V? So delta V is there, what is delta I? Yeah, so that is the reason ideal current source got infinite impedance. And then, but when it comes to transistor, the problem is it is not ideal. If you don't take into Early effect, then what will happen is this is your VC, this is your IC. Then for ideal transistor means no Early effect. See, in the active region it is a straight line. So delta VC by delta IC, which is equal to 0. So ideal transistor got infinite impedance, or it's the current source got when you are operating transistor as a current source, it got infinite impedance. But the problem is because you got Early effect, it got a impedance which is equal to RO. So the RO is the impedance of the current source. See, RO is the impedance of the current source. So Gm V pi and RO is the impedance of the current source. So when we take into account Early effect, So when you take into account early effect, it's easy. RC, then you are connecting a resistance RO, and then that is between these 2 points in parallel with the current source, and then this is the impedance of the current source RO. So small signal model without early effect, with early effect. So this is the only difference. So then when you draw, this is without with early effect. So with early effect means the difference is only you connect this RO and then RO, which is equal to delta VC by delta IC, which is equal to VA by IS into exponential VB by VT, because IC equal to IS into exponential VB by VT, and then which is equal to VA by IC. So your output impedance or impedance of the current source. Mostly RO we call it as impedance or impedance, output impedance. But then impedance, later we will call this RO as the impedance of the current source. So for time being, both are correct. This RO is the impedance of the current source or output impedance, because when you see your signal here will see impedance as RO. Or when we look from here, from outside to inside, you see impedance as RO. So your output impedance equal to VA by IC. That is depending upon your early voltage and IC, which makes sense. When you have when you don't have early effect, what is the value of early voltage? When you don't have a early effect, what will be the early voltage? Infinity. So that's the reason your RO will become infinity, because your VA will become infinity. So that's the reason RO will become infinity. So small signal model can incorporate a resistance term RO, then you get a small signal with early effect. So now we are going to see without early effect. So we will be dealing without early effect, then with early effect. After some time, we will do everything with early effect, because without early effect is an ideal situation. So here we have connected 800 millivolt. That is for this 800 millivolt is for keeping bias, forward bias between base and the emitter. And then this VCC is for keeping reverse bias between collector and the base. And then this is your signal. Then you can draw, see your DC voltage source anyway we will be grounding. So that's the reason here you got to ground, and then this is your V1. Your signal, we will not ground it because this is changing with respect to time. And then you got R pi, and then from here you got to ground, and then between collector and the emitter you got the current source GM V pi, and then from here you are getting output, see RC. After 100 ohm you got this DC voltage that is not changing with respect to time, so that we ground it. That's the reason we grounded. And then this is your V out. V out is between collector and the emitter, this ground, see, between these two ground. These all grounds are connected to same point. In this example, a resistor is placed between the power supply and the collector, therefore providing an output voltage. See, you can get an output voltage, because this output voltage we are measuring this voltage. So here we are measuring voltage between this point and the ground. Then actually what we are measuring is a voltage drop across this RC, because this point is same as this point, this ground is same as this ground. Small signal model example. So this is what we have drawn, but when you bend it down, just this is because with respect to this line you can rotate this RC and then bring it down, then you can get a clear picture. So when you measure the output voltage, actually you are measuring with early effect. Then you got this RC, this RO, see both are coming in parallel, because this is ground, this is a ground. So RC and RO. So basically you are measuring the voltage drop across this parallel combination, RC parallel RO, when you have early effect. When you don't have early effect, RO equal to infinity, so this part is open, and then what you are measuring is a voltage drop across this RC. So this is for NPN, and then we got PNP transistor. And then this is for PNP. So NPN and PNP got the same small signal model. So when you draw NPN, so V in, and again you got R pi, then you ground it, and then see, please remember when you put this positive, this negative, the current direction is down. You can put maybe this positive, this negative, then it should be up. But then I have put this positive, this negative to make this down, but you can put maybe this negative, this positive, you can make it up. It's up to you. Then for PNP, so PNP you get the same small signal, V in, R pi, GM V pi, R RC B out. This was one of the exercises I asked you to do at home. So did you find both are same? Could you get both NPN and PNP same small signal? If you got it, that is good. So you should get both same. NPN and PNP got same small signal. Then this type representation, I think some of you might confused. When you have PNP, you are putting here VCC, but then here you got VCC, but actually this is not collector, this is emitter. So in the Rasavi's textbook, I don't know, if you studied a transistor previously, then you may have some issue when you represent this way, means when you see for the first time. So you got NPN, NPN. So when you have NPN transistor, you need a forward bias between base and the emitter. So this is your base, this is emitter. And then reverse bias between collector and the base. So here what we will be connecting is, we will be connecting a positive charge because you want a reverse bias. You know what I meant? So this is NPN. So then this I will be representing in a simple way. So this I will be grounding, maybe I will be grounding here. So here I got a V in, here I got a V in, and then here I will be representing, so this is maybe plus 5 volt. So I will write that is equal to VCC. So I will be writing VCC. So that is a simple representation this way. But then when you have PNP, so the PNP, this arrow is up, and then this is the direction of the current. Here the current direction is like this. That is the reason this arrow represents the direction of the current. But then PNP, PNP, and then this is a base, this is a emitter, this is a collector. So PNP, what voltage I should be connecting here? In order to make a reverse bias between collector and the base, so what voltage I should be drawing? Negative. So here I will be connecting, so negative voltage. Something like this. Or here I will be connecting these two, I can join together because both are ground. Yeah, so then this is a representation, but then see, emitter you are connecting to positive, collector you are connecting to the ground. So or I can represent, what I can do is this, another way of representing is I can rotate it. So when I rotate it, what will happen is, still I got the PNP, then this time now become, what is this one? Emitter. Then I took my collector here, and then this is the base, but still it is PNP, PNP. And then what I can do is here, what voltage you will be connecting? No, this emitter. See, so you can connect here positive, and then you can say that this is your VCC, and then this part you can ground it. So this, then the advantage of this one is, see, both are kind of consistent in the drawing. But the advantage of this one is kind of consistent. The top you got VCC, top you got VCC, here you are grounding, here you are grounding. But then please make sure that you understand the drawing, because here this is collector, but when you draw like this for PNP, this is emitter. That's the only thing you have to be careful. Small signal models are identical for NPN and PNP. Then the equations. So the equations are for PNP. So PNP transistor, again, see, I have drawn like this. See, you can see here PNP. So here it is negative, then here it is positive, and then so PNP transistor, your IC equal to IS into exponential, not VB, VEB, because VEB, VE minus VB by VT, and then same like, so we don't write VB, means for example I'll get NPN. So NPN equal to VB, voltage between base and the emitter. Here we call it as voltage between emitter and the base. VEB means VE minus VB. VB means VB minus VE, means voltage at the base minus voltage at the emitter. So why we are writing like this? For a PNP transistor, voltage at the emitter, see this voltage is higher than voltage at the base. So that's the reason we write VE minus VB, because here it is positive, here it is negative. So that's the reason we write VEB, means voltage emitter minus voltage minus VB. So that is then here for NPN, this is more positive, this is negative. So that is VB minus VE. And then when you have early effect, your collector current. If you don't have any early effect, your collector current equal to Is into exponential VEB by VT, same as NPN, VB by VT, only that difference. But then when you have early effect, you have to add one more term, that is equal to 1 plus VEC by VA. For NPN, 1 plus VC, sorry, this should be VCE by VA for NPN. So this is EC is fine, here is CE, VCE by VA for NPN transistor. With the polarities of emitter, collector and base reversed, a PNP transistor is formed. All the principles that applied to NPNs also apply to PNPs. Means all the effect that you are getting with NPN, you will get with PNP. Only the equations are different a little bit, biasing you have to give accordingly. With exception that emitter is at a higher potential than base and base at a higher potential than collector. Means when it is a PNP, then you have to make sure that even in the PNP we follow the same rule. Even if it is in the PNP, you have to make sure that the base and the emitter should be forward biased. So you have to give voltage biasing accordingly. Base and the collector should be reverse biased. So if I were you, what I would think is I don't care about the NPN or PNP. I just got the transistor, then I will find out which is the base, which is the emitter, which is the collector. Then I will provide the biasing accordingly. I need forward voltage between base and the emitter. I need a reverse bias between base and the collector. Then you connect the voltage accordingly. So comparison between NPN and PNP. So this is another advantage. When you have NPN and PNP in the same circuit, if you follow this kind of inverted mode, then you can give same bias. Drawing is easy. Otherwise, what will happen is for this one you draw a separate circuit, this one you draw a separate circuit and connect the bias. But if you rotate it and then if you bring the emitter here, then you can connect the same voltage. See, both the circuits, now it is under a proper bias. But then you have to reverse it, as I said. Then it is easy. So that is the reason the Rasavi's textbook you will see this way. Emitter is up for the PNP, but maybe in the other textbook like Sedra, Smith, they might be using down, emitter down for PNP. Like this is NPN, emitter is down. For PNP also they will draw in the same way and then put the arrow up here going inward. But the Rasavi, what he does is he just rotate the transistor and bring the emitter up and the collector down. The advantage is then you can connect to see both NPN and PNP in the same circuit. Then comparison between NPN and PNP transistors in the active mode. So this is a NPN transistor active mode. Your collector got more positive than here, see, base. And then for PNP, so PNP here this base got more positive than your collector. Edge of saturation, emitter, base and collector voltages are same. Edge of saturation, same thing. Base and collector voltages are same. So that is this edge of saturation. Edge of saturation. So in the saturation region for PNP, your collector is more negative and then than your base. Base is positive, so collector is more negative. For NPN, your collector is more positive than your base. Saturation mode. Saturation mode means your base is more positive and then your collector is less negative. Means this is our forward bias. So this is becoming forward bias. In the saturation mode, your base is more negative than collector for PNP. So you can just think, see, this is forward bias. Your junction base and the collector is getting a forward bias here. So how to amplify voltage using BJT? So we will be studying voltage amplifier first. That is our maybe one of the main applications of transistors is making voltage amplifiers. So we will be studying voltage amplification. And then as I said, transistor is a voltage controlled current source. When you are driving a transistor, you are varying the input voltage, then you are varying the current. You don't get voltage at the output in the transistor. But then we connect a resistor and then convert the current into voltage. So that is the reason we get voltage amplification. Otherwise, using transistor, you get only current amplification. So you connect a resistor and then you drop the current across the resistor and making a transistor a voltage amplifier. Means here you have a small voltage variation, then you get amplified output here. So voltage amplifier. So we will be studying voltage amplifier. So voltage amplifier is required in many places. In all the front-end electronics, you need amplification of the signal. So I'm taking a simple example, that is an audio amplifier. We will be taking an audio amplifier as an example because you will be breadboarding an audio amplifier and then you will be amplifying some signals. So audio amplifier. So in the audio amplifier, you got the microphone, then you got the amplifier, then you got the speaker. Because microphone signal that is very, very small, maybe in microvolt, then you amplify, then you connect your speaker, then only you can you will be amplified and you can hear properly. In the audio amplifier, when you design an amplifier, then now we are talking about a voltage amplifier. So these are the rules of voltage amplifier. So when you design the voltage amplifier, the problem is you should know many factors, not just the gain, because most of the time people are often thinking only about gain. So when you say, okay, voltage amplifier, I designed for 10, my amplification is 10, because here without connecting to the microphone, you can measure the voltage of this microphone. Output voltage, you found out maybe you got 1 microvolt, then you need maybe 10 microvolt. Then what you do is you design an amplifier, voltage amplifier with gain 10, and then you said, okay, we got the gain 10, but the problem is when you connect it to here, you don't get this gain 10. Why? Because you have to take into account input impedance, you have to take into account output impedance. So when you design voltage amplifier, there are other factors like input impedance, output impedance, all these things will come into picture, not only gain. And this is an example. So you got a microphone, and then the microphone I represent something like this. So microphone got a varying voltage. This is the output stage. So when I look from here to inside the microphone, what I see is a microphone got some output impedance. Microphone got some output impedance, maybe that is around 200 ohms, and then microphone is generating some voltage signal. Because microphone, here I got microphone, what will happen is, see the microphone, my sound is going and hitting here, there got some diaphragm, then you got the coils, magnet, and then it is generating some voltage. So with respect to sound, it is generating some voltage. So then that's the reason here we are not taking into account all the diaphragm. So when I look the microphone, this is the output part. When I look into the microphone, what I see is I can see some output impedance, and then some voltage is coming out through that connection, maybe a track, copper track, and then that is proportional to the sound. So maybe I have got a 10 millivolt voltage signal due to some sound. And then when you look into the microphone, the connection, then you got 200 ohm output impedance, and then that you will be connecting to your amplifier. Then when you connect that into the amplifier, then your input impedance of the amplifier plays a big role. Why? Because input and output impedance of an amplifier play a critical role in its capability to interface with the preceding and the following stages, which is very important. This is an example. So now when you connect your amplifier, this is your voltage amplifier. When you connect to the voltage amplifier, then 200 ohm, you already got it, because this part is coming from the microphone. Then input impedance of your amplifier is Rin, so that I represent it as Rin. Then you have connected. Then what will happen is your actual voltage to the microphone is not 10 millivolt, because you got a resistor here, you got a resistor here. You know, then there will be a voltage drop. So this is acting as a resistor divider or a voltage divider here. See, then your actual voltage to the microphone here, actual voltage to the amplifier is V1. So V1 equal to Rin divided by Rin plus Rm. So this is Rm, resistance of the microphone, into Vm. That is a voltage coming from the microphone. So that is the reason, because of this equation. So if you got your input impedance of your microphone, that is coming into picture. That is the reason you designed for gain 10, but then you are getting gain maybe 5. Why? Because your input signal, you thought 10 millivolt is coming to the amplifier input. Actually, you don't get 10 millivolt. Here you got 10 millivolt. Here you are getting a fraction of 10 millivolt because of this voltage division. So then you have to take into account your input impedance. Then I will ask you a question. So this is a problem. Then somebody will ask you, then what is the ideal input impedance of a voltage amplifier? So two answers. One is 0, one is infinity. So 0, how many? Infinity. Yep. So infinity. That's the reason the ideal voltage amplifier should have a very high input impedance. That is the reason in the operation amplifier, when you check, the input impedance is a very big value. They will provide it. This is our input impedance, big value. so that you are not losing any signal when you connect your operation amplifier. So this is I am talking about a transistor based amplifier. For that also it is very important. The input impedance should be very high. For example, some value, if you put in some values which make sense, if your input impedance is equal to 500 ohms, you only get V1 0.7, 70% of the signal only you get it. And then if it is 2 kilo ohm, then you get 0.9% of your signal here. Then output impedance, again the amplifier got output impedance, and then you are going to connect your speaker. Then the speaker is an interesting device. Speaker got a very small impedance at the input. So most of the time it is around 8 ohms, 5 ohms. That is the input impedance of a speaker. Why? Because you got a coil inside in the speaker, because the speaker is operating just opposite of a microphone, because you are giving the signal and then the diaphragm is vibrating. You are driving using the signal, then the diaphragm is vibrating and then you hear the sound. Then you got the coil, the coil is there, magnet is there, and then when the current is going through the coil only, that is vibration happening. Because of that your input impedance to the speaker is very small, maybe 8 ohms, sometimes it is 10 ohms, sometimes it is 6 ohms. And then when you have some 6 ohms you are connecting, then what you are doing is you made an amplifier, then you are connecting to a speaker. If the speaker got input impedance 8 ohm, means what is happening is literally you are kind of shorting. Not really shorting, but you are then very high current will pass through. And then, so again you are seeing R amp, so that is your output impedance. Then 8 ohms, here you got 8 ohms here. Then what will happen is your V out, your output voltage equal to RL by RL plus R amplifier. So again you are getting some amplified voltage, but then actually when it comes to the speaker, when you don't have the speaker, your output voltage is maybe 10, maybe 100 millivolt. So here you may get 100 millivolt when you don't connect the speaker, but when you connect your speaker, you don't get 100 millivolt, you may get 50 millivolt. Then you might be scratching your head. I designed for 100 millivolt, I measured using oscilloscope. Without connecting speaker, I got 100 millivolt. When I connect, my voltage dropped. That is because of this input impedance of the speaker. So then that is equal to 8 ohms. Then V out equal to RL by RL plus R amp. So that is your voltage. I can put in some values. If your amplifier got 10 ohms, if your amplifier got 10 ohms, what will happen is your output is just half. If your amplifier equal 2 ohms, then you can get around 0.8 volt. See, then think about your output impedance of the amplifier equal to 100 ohms. Then you will be losing lots of signal, because you are getting some signal, and then if your output impedance of the op amp equal to around 10 ohms, and then your speaker got input impedance 8 ohm, what will happen is you are losing more than 50% of the signal. It will come out of the amplifier, but to the input of the speaker only 0.4 only going in. Then what is ideal output impedance? Yeah, so ideal voltage amplifier got infinite input impedance and then 0 output impedance. Again, when you read operation amplifier data sheet, you will find out the output impedance they will write very small value, but we can't get 0. That is ideal case. So that is the reason when we design a voltage amplifier, we have to make sure that our input impedance is very high, then output impedance is very small. So ideal voltage amplifier, input impedance is infinite and output impedance is 0. But in reality, input or output impedances depart from their ideal values. Next section is input output impedances. We discussed about input output impedances. Now my question is how will you calculate input and output impedances of a circuit? Because then only you designed your circuit, how will you calculate it? So that maybe we will continue in the next lecture. Input and output impedances, how to measure.
down to up, I think. Why?
It is positive, negative, it will be always down.
But this is not ground.
Yeah, I draw you.
Yeah, and this is the collector. So the collector is the ground and the current is the up.
Yeah, no, please come. Mix that outside.
Yes, absolutely. Maybe give it a couple of minutes for them to sort of arrive, and then because we don't get taped between 12 and 12:05, but 12:05 is the thing, so you've got there's perfect time there while we're waiting for the thing to come on. So. Yeah, the second is.
We've got the industry night coming up on the 27th. It's a good opportunity for undergrads as well as postgrads to interact with the professionals.
Could you send me some details of it? Because if you send me the details of the night, I can put that up on LMS and just let all these guys know, or is it up on the faculty website?
I sent to you by email.
Yep. Okay.
There are a couple of
The key dates.
attached.
Okay. Yep.
And there's one poster attached, which
Okay.
I'm just going to put up. So if you could just